can go straight to the first lecture of Professor Sanpera. Please, Professor.
Yes, thank you very much. And welcome to this last lecture of mine. Okay, so I just wanted to show you that we have done a lot of work. I want to summarize what we have been doing up to date. So this is the last lecture, and the level is increasing on difficulty, but I just wanted to show you that we have done quite a lot of things. So many things that it's very difficult. So first of all, up to now, what have we been doing in these 2 days? So first we learned how to describe states of composite systems via the tensor product. Then we learned that we have something called the Schmidt decomposition, that it works for pure bipartite quantum states. Then we have learned how to use the marginals, or the reduced density matrices of the pure composite system, okay? So when I put it as a density matrix to determine if a pure state is separable or entanglement, this is the consequences of the Schmidt decomposition. Then we have introduced the ensembles of pure quantum states, and we have described them with the density operator. Then we described, I think it was yesterday already, I don't know, it's Thursday in a row, no? You are not going to see me more, so you should relax. Okay, so we described how is the convex set of quantum states and the extremal points. So we were saying that this is everything, many things in quantum information and quantum sets, and that the extremal points were projectors, pure states, or grand efficient density matrices. Then we have defined the properties of an entanglement measure. It must fulfill in order to be an entanglement measurement. We have introduced which is entanglement entropy, which we say is a proper measure for bipartite pure states, okay, as a function of the von Neumann entropy. Then we introduce, and we say for mixed states where the things are start to be complicated, we have a measure which is the concurrence that I didn't explain, but I say it exists. And this is the important thing to know that there is a measure. And we say that if we go for higher things, so not qubits by qubits, we have also a measure which is called negativity, okay? And I say that today I will explain where it comes, this negativity, which is a good measure for MPPT kind of states. And then finally, we introduce some measurements that we say some of them they are operational and some of them they are geometrical and so on and so forth. So this is what we did these 2 days, which is quite a lot. And this is the last lecture. And this is a little bit, I don't know if it's very rational that first I say how are the measures of entanglement, and now I want to answer, it's my state entangled or not. So probably the logical order is the other one, but it has also sense to do it like that. So what we are going to do today. So today we are going to learn about entanglement criteria, operational criteria, non-operational, quantum maps, the Schmidt number for, if we have time, for mixed bipartite states. And I hope that I will convince you that you have, if you belong to a church, it should be the church of the Hilbert space. It's the most funny church, I think. Okay, so let's go to what we are going to answer today. What we wanted to answer is the following. If I give you a state, bipartite, multipartite, it will be Gottfried who will answer these questions. Is my state separable or not? Well, this innocent question is not innocent at all. Okay? And then there is these things that I'm always confused, but I have to write it because if not I say it the other way around. So we have necessary conditions, and a condition is necessary, it means that it has to be satisfied, but if it's satisfied alone doesn't guarantee that the statement is true, and we have sufficient conditions, which if it is satisfied, guarantees the statement is true, but not fulfilling it doesn't mean necessarily that the statement is false. And indeed, the characterization, verification, and detection of entanglement is crucial. It's crucial for everybody who is going to do quantum, or who is doing things with quantum information or quantum technology, but also for other things, and this is what I would like to end up my lecture with. So what we have to do today is trying to find that, okay? If there is sufficient and necessary entanglement criteria for bipartite mixed states. And we will see that in very few cases we have sufficient and necessary. Normally we have sufficient but not necessary. Necessary, not sufficient. I don't know, I never know these things. We will see, okay? So for bipartite pure states, everything is solved. We have done it these days. So I give you a bipartite state which is composite, and we know everything because you have the Schmidt, the composition. It doesn't matter, the dimension has to be finite. If it's not finite, there are things when Eugene Polchek is coming which are equivalent, okay, but it's not exactly the Schmidt. And then we look at the Schmidt rank. If the Schmidt rank is 1, the state is not entangled. If it's higher than 1, it's entangled. And on top of that, the Schmidt coefficients gives us a measurement because it's entanglement entropy. So everything is done. So the only funny thing is to go to bipartite states for bipartite systems, okay, to go to mixed states. And then we have a lot of criteria. And I'm going just to use a couple of criteria because there is a list, exhaustive list of criteria. So for instance, let's start by this one. We have something which is called entropy entanglement criterion. And we say state rho B is separable if verifies the following. So if it's separable, it's not an if and only if, okay? So the entropy, the von Neumann entropy of the whole system has to be bigger, this is a number, than the von Neumann of the reduced density matrices, okay? Well, this is the von Neumann, so minus trace rho log rho. Okay, so what does it mean that? Okay, so if the state is separable, what it's telling us, it's separable, okay? So all the things that we have there, it's classical correlations, okay? And these classical correlations, they are embedded in the bipartite system, not in the single one. So therefore, this is a condition which is sufficient if that happens to know the state is separable, but it doesn't have to be necessary. So there are many of these conditions which are not so interesting, and I want to go to the conditions that they are a little bit more interesting, which are the following ones, okay? So the first criterion that we are going to use, it's called the PPT criterion, and we say that if a state is separable, so it doesn't have entanglement, it has to fulfill that the partial transposition, PPT, of the reduced density matrices, it's positive, okay? And then we were using that in order to show what is the negativity, so I just put it here, okay? So if I have a density matrix, it's an operator, it's a matrix, okay? It's a composite, so it has 4 indices, okay? Because it comes from Alice and Bob. But mathematically, it's not here, it's this matrix of here, okay? To transpose means that I transpose partially only one of the systems, okay? So in this case, if I transpose respect to Alice, I have to flip files and columns which corresponds to Alice. Okay, and there is exactly the same definition for Bob. And if one of them is positive, the other one is positive. So it doesn't matter which one do you want to choose. So I just put here an example so that you see it's very simple. I'm going to transpose this density matrix, it's 2 qubits, so it's a matrix 4 by 4, completely generical. I didn't put any condition, it has to be admission, so I put the admission, but I didn't put that the trace is 1, doesn't matter. And I have to transpose with respect to Bob. So if I transpose with respect to Bob, this is Alice, this is Bob, Alice, Bob, so I have transposed. So this Alice, Bob once goes here, and it once goes here. This corresponds to the following. I take these small matrices, I divide it by 2, okay, and I flip these 2. I flip these 2, I flip these 2, and I flip these 2. And I have my matrix, okay? And now I look at the density matrix. So why this important? This criterion is important. What does it mean physically? Okay, it means physically the following. There is, and this is why it's important and why it's so powerful, there is a theorem, which is Wigner theorem, which tells us that transformations in quantum mechanics have to be unitary or anti-unitary. That doesn't matter. So unitary is UU data, it's equal to 1. Okay, this is the definition of a unitary matrix and anti-unitary matrix is that. They are equally good one to another. Okay, so typically you use an anti-unitary matrix, for instance, when you do charge conjugation, time reversal. This is an anti-unitary matrix. Okay, so PPT, what is it? PPT is a criterion that tells us just transposing, okay? It's to do an anti-unitary matrix. It's like time reversal, charge conjugation, one of the systems. So if I have my system like that, PPT is telling me, do in the first system a unitary transformation and in the second an anti-unitary transformation. Well, this is crazy because a priori that doesn't work, no? So imagine that this is separable, so we have a system which is separable. I have my part, I'm Alice, I have a part, and somebody has Bob, but our systems, they are not correlated. And now I do an anti-unitary transformation to me, that's fine. I reverse time, that's fine. This is quantum mechanics allows us. And Bob doesn't reverse it, well, that's fine. Because if the state is separable, okay, so if my state is row 1 for Alice and row 2 for Bob, and I do this kind of partial transposition, what I'm doing is Alice evolves according to a unitary transformation and Wigner tells us, okay, and Bob evolves according an anti-unitary transformation and Wigner tells us it's okay. But if Bob and Alice, they are together, okay, so this is a system which is correlated, what I'm saying is, okay, Alice, you have your arrow of time if you want in this direction, and Bob reverse the arrow of time. And look if this is physical or not. Well, a priori, this is absolutely not physical, right? Because combining a unitary with an anti-unitary is neither unitary, neither anti-unitary. So this quantum mechanics doesn't allow to do it. So there are many systems that when you do that, okay, they say, hey, I'm not a system anymore. Okay, so what happens? That the result of doing this operation, it's that whatever matrix is there, it's not defined positive. So if a matrix is not defined positive, it's not a physical system. So this is a flag, all right? And it's very logical. And we could do it with any other, but all anti-unitary matrices are proportional to transposition. So it doesn't matter if you want to do charge, or when you do, people, if somebody here from high energy physics, when they do CPT, violation, and all these things, this is the same. Okay, so this is a very strong thing. Okay, so recall that a matrix, okay, it's defined positive if all the eigenvalues are larger or equal to 0. So if I have a density matrix bipartite and I ask you, listen, is this a state entangled or not? The first thing that you should do is partial transposition. Respect to Alice or with respect to Bob, doesn't matter, it's the same. If I have that my matrix is not anymore a matrix, this state was entangled, for sure. Okay. However, fortunately, yes.
When you write down how to do the partial transposition, you specifically set up a base there, right?
Yes.
It doesn't matter.
No, it matters. Take the computational base, okay? Because imagine that I take a base, okay, in which I have put my matrix, which is not complete. I have to have something which I know what is to change, okay? So imagine that I take a base in which the matrix is already diagonal. I cannot transpose anything. So you have to do it, this is a very good question, you have to do it with respect to the computational basis. So you write it in the computational basis, your matrix, and then you change it, okay? Because you have, if you take a basis which is not a product vector, computational basis is 0, 0, 0, 1, 1, 0, 1, 1. If it's not a computational, it's not a product vector, you don't know how to do the transposition. So it has to be written in the computational basis. So a good question. Okay, so unfortunately, because if not, I will not be here, okay, for me, fortunately, this theorem, it's only sufficient and necessary if I have 2 qubits or I have 1 qubit and 1 qubit. Okay, in these cases, and only in these cases, if my state is MPT in front of partial transposition, it's entangled. Okay? But in higher dimensions, if I have 2 qubits, okay, of dimension D bigger than 3, bigger or equal than 3, so 3, 3, 3, 4, whatever, 2, 4, 2, 5, this is not sufficient and necessary. It's sufficient, but it's not necessary. Which means the following. it means that they are states, okay? So, okay, it's necessary, but not sufficient. I don't know, probably, I'm sorry, I'm a little bit dyslexic, and with sufficient and necessary I'm very bad. But you will understand it, okay? It's necessary, but I don't know. What I want to say is that it can be that there are states which are entangled, which fulfill that when I do the transposition, they are positive, okay? And nevertheless, they are entangled, okay? So it will never happen in C2, 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 C3, but in higher dimensions will happen. Well, this is very nice, because I was yesterday putting some graphs saying how is the states, okay? Well, the states in general, bipartite, multipartite, doesn't matter, okay? They are going to be like that, okay? So there are some states which they don't have any quantum correlation. They have classical correlated, they are density matrices. There are some states that they are entangled, but they are PPT. Okay, so if I do partial transposition, I don't see anything, it's positive. And then there are many states which are MPT entangled. In front of PPT, they become negative. Okay? And we have this classification. And now, if I give you a state which is here, well, it's trivial that you see if it's MPT or not. You do partial transposition and that's it. But if I give you a state which is here, how you are going to see if it's separable or PPT entangled? Well, this is an NP-hard problem, okay? And we know some things, but a priori an NP-hard problem means they don't have solution, okay? Or it's non-polynomically hard. So, and then for that we need other criteria. And the first criteria that we are going to use, so this criteria of MPT, PPT, I was saying it's a criteria which it's operational, okay? In the sense that I take a state, and on this state I do something, okay? It depends on the state. But I have criteria, and we are going to see some of them now, which they do not depend on that, okay? And the first criteria, which is very nice, is this one, okay? So there are entanglement criteria that depend, and there are other ones that they do not depend, okay? And this is a small lemma that I need, but it's not very important. And what we are going to do is, again, let's do in physics. So we have convex set. This is our convex set, because if I'm here, PPT states, okay, all PPT, separable and entangled, this is a convex set, okay? MPT, it's not convex, because I have to take out all these things, so it's like a moon, all right? So clearly it's not convex. But what I want to do is the following. I want to say that if I have a convex set, which is compact, which means, remember, convex and the border belongs to the set, okay? In a finite dimensional Banach space, then I know that if I have a point which is outside of this convex set, it must be a hyperplane that separates that. It's completely geometric picture, no? So I have an egg, a void egg, inside of the void egg I have the yellow thing, which is also convex, and for sure I can separate it between the yellow and the white part, okay? So I can make with my knife cutting so that I only get that. It should be like that. So therefore, we want to know if we have this point which is outside of the separable ones, okay? For sure it should be a hyperplane. I can find a hyperplane because the dimensions are very high. It's a plane in higher dimensions that separates this point from this convex set. Okay? And this is what we use normally. So we say that we call it entanglement witness. Okay? So there is an operator, it's this hyperplane. It's an Hermitian operator, so it's an observable, okay? And it's called an entanglement witness if and only if fulfills the following. So the expectation value of this operator, okay, which is my witness, on all the states which are separable, so on this side, it's for sure positive. And it exists at least one entangled state, this one, which is on the other side of the plane, for which the expectation value of this operator will be negative. If I have an operator which can have an expectation value which is negative, this operator cannot be defined positive, okay? Because rho is a defined positive thing. So I have an operator, the witness, which is a mission that it's not defined positive and it's able to detect some states. This is maybe the best definition of an entangled state. So we were always saying an entangled state is something that it's contrary to something which is separable. But we have a definition here which is a little bit better, not much better. An entangled state is entangled if and only if there exists an operator, which we call an entanglement witness, that detects it. Okay. So, and we will be using that quite a lot. So, this is what we have. And now I'm going to say something like that. This entanglement witness, and we will come back to that later, okay? We will call it the composable, and I will explain you why. It means that if and only if I can write this emission operator, which is not positive defined, as the sum of two operators, P and Q, which are definitely positive, okay? But I can write W, my witness, like Q to the partial transpose. So let's think in mathematics. W, my witness, is a matrix, and I'm saying, okay, this matrix, I can write it like the sum of two matrices, okay? P and Q transpose. But Q has to be positive, and you will understand later why it is like that, okay? In case that it's like that, that my witness, I can write it like that, okay? I will say that my witness cannot detect any PPT entangled state. It's like that, okay? So, these kind of witnesses, they only detect non-PPT entangled states, which I already know that is MPPT because I do the partial transposition of it. But it's important for that. Okay? So I can say, well, following here I can say, yes, I know that rho, this is the full theorem, rho is an entangled state if and only if there is a witness that detects it. Rho is an entangled PPT state if and only if there exists a non-decomposable, so I cannot write it like that, entangled witness that it detects. And rho is a separable state if and only if the expectation value of any entanglement witness is positive always for this state, for all entanglement witnesses. So there is not an entanglement witnesses that can see a separable state. Okay, so indeed I can write my entanglement witnesses and my space in the following way. So I have states which are separable, this one over here. I have states which are PPT, and I have states which are MPT. This witness of here, the first one, will be able to detect all these states, whatever is there, PPT and MPT, all these ones, okay? So this is a non-decomposable witness because at least it detects these ones. And this other witness, it's a decomposable and it will detect all these states. And it will be positive on this part of the Hilbert space. Okay, so we could solve this problem if we know how to find all these witnesses. But if I told you that the problem is that this problem is empty hard, that means that we cannot find all these witnesses. Okay? So, how do I construct an entanglement witness? Let me give you a very simple case. Okay? Imagine that I want to detect now a state which I know already because it's a singlet, that I want to show you how it works. So let's just construct a witness for this bipartite pure maximal entangled state, which is a bell state 0, 0 plus 1, 1. Okay? So I can construct a witness operator that I'm going to do it like that. I take my bell state and I transpose my bell state, partial transpose. So this is my bell state because it's 0, 0, 0, 0, 1 half, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1. This is a 0, sorry, this is an error. Okay, another error. Okay? So now I have to partial transpose, and I told you that you partial transpose just moving the diagonal, so this is the partial transposition. And this state, if I look, this is a 0, okay, it's a mistake. This state is exactly like that, 1 minus 2 times the singlet. Okay? And I say this state, it's an entanglement witness. Let me show you how I see it. Okay? So if it's an entanglement witness, I say that it has to be positive over all separable states. How many separable states I have? Infinite. So I'm not going to try all separable states. But a separable state, I have defined that it can be written as a convex combination of projectors on product states. So if it's separable in one projector, generic projector in product states is separable for all separate, it's positive for all separable states. So instead of looking at this thing of here, what I have to do is just look how is the trace of my witness with a single one product state, EF, okay? And this is exactly the expectation value of this guy over here. So what do I have to do? Well, I write E as the most possible, most generic qubit, A00 plus B01. I write F as another generic qubit, A10, B1. And now I pull it here, and then it's trivial to show that this is always positive. Why? Because this witness is 1 minus 2 times the singlet. And at most, the product state at most will have a superposition of 1/2 with this guy of here. Okay, so it will be 0. It's very simple. Okay, and now I want to say that there exists at least one entangled state which is detected by this witness. Well, if I go here, it's trivial, no? Which is the entangled state that it will be detected by this witness? The singlet. Okay, because the singlet will give me 1 minus 2 minus 1. So, and indeed, I do this thing, and then I see that trivially the singlet is detected. So to construct witnesses is easy. Normally it's very easy for easy cases, okay? Because this witness is decomposable. I can write it like P, which is 0 with a semi-definite positive operator plus a transpose. Okay, so this is P equal to 0 plus Q. Q is positive because this is a positive operator transpose. So it's decomposable. So now I want to tell you that I have talked about two things which looks very different, which is PPT, entanglement, and I was telling this, and this is related to time transversal, to time reversal, unitary, anti-unitary, and so on, and entanglement witness. So have these two things something to do in between? And I would say yes, okay? So this is not a casual thing, it's much more deep. And how do I see that? Well, how do we see? We start by this theorem of here. So, as a state, bipartite, I don't care, qubits, qubits, okay, is entangled if, and only if, there exists a positive map which goes from B to C such that, and I will go in detail to that, the identity acting on my superspace A and the map as acting on the superspace B, it's not defined positive. Okay? So when we see something like this, what that has to do? Well, this is the following. I was telling you yesterday, so for isolated systems, we only have unitary evolutions. But if the system is not isolated, we don't have unitary evolutions. We have more general evolutions. This is a quantum map, quantum channel, a quantum operator, whatever, it's the same thing. So how these guys are, okay? So if I want to define what is a quantum operator, I will say that it's something which is described by a completely positive trace-preserving. What is this thing? Well, a completely positive trace-preserving map, it's a map. A map is a transformation between operators and operators, okay? Which is, first of all, positive, because if I apply my map to a density matrix, and this has to be physical, I have to obtain a density matrix, okay? It will not be physical. 2, it has to be trace preserving, okay? So the trace, if the trace of rho is equal to 1, the trace of the state that I get after applying my map has to be equal to 1. So I cannot lose or create particles on this process. It has to be linear, because quantum mechanics is linear. So applying the map to a convex combination of states has to be equal to the convex combination of the states obtained after applying the map. Okay? Because again, this preserves all the properties that I will have. And finally, it has to be completely positive. And completely positive means the following. I have my bipartite state which acts Alice and Bob, okay, on this Hilbert space, and it's a state, so therefore it's defined positive, and therefore it's admission, pam, 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 pam. Then I require that when I apply the identity on Alice, so I do nothing on Alice, and this map on Bob, this has to be a positive map. Okay? So this condition of a quantum operation is the extension of a unitary evolution in high dimension, in open systems or closed systems. Okay? So if the system is isolated, this will be exactly like a unitary evolution. If the system is not isolated, it will be described like that. So what is this completely positive means? Why we have to do that? Well, because the structure of the tensorial product, no? Because it tells the following, no? Suppose that Alice and Bob now they share this entangled state, 0, 0 plus 1, 1. And Alice makes something on her part of the system, okay? So what does it mean? That, of course, Alice can do something on her system, or let's say in this case, Bob does something on his system, so it applies an operation. Alice does nothing, and the result has to be a physical system, because if not, it would be very strange, no? So we have an entangled state, okay, which can be two, I don't know, a hydrogen atom with there is an electron in my hydrogen atom, and somebody takes this electron. Okay, this electron is entangled with the proton. Okay, it's not an electron that it comes, it's entangled because it comes from a hydrogen atom. But this electron is given to Bob, and Bob decides in his office that it works. I don't know, it's going to measure the spin of this electron. But it cannot be that that brings my state, okay? So I still have a proton and a neutron. Okay? So maybe things will change, but it has to be physical. This is what it's asking. So if in a bipartite system, one of the parties doesn't do anything, okay, that doesn't mean the system, if it's a low operation, has to be defined positive. So this is what it means completely positive. And indeed, if completely positive was not possible, that means that we will be able to signal faster than light, which is not possible. Okay? So we will write it like that. So we will say that a quantum map, and the quantum map always acts on the system, okay? It's called also K positive, okay? And now I'm going to go a little bit more picky. It will be K positive if the induced map, which is do the identity on K, which is a Hilbert space of dimension K, and then, which acts like that, so, and my map acts on Hn, so this is a map that it goes from say K times bounded operators of dimension n to say K bounded operations of dimension n. That doesn't matter if this is positive, okay? And now I would say, if this is positive for all possible values of K, I will call that this is completely positive. So if I have a map which is physical, which is describing a quantum channel, an operator, whatever, it has to be completely positive. For any value of K, okay, it has to be completely positive. But we will need this definition. Okay, so now I want to show that an entanglement criterion, okay, and in particular, they correspond to maps which are positive, but they are not completely positive. Because what I'm doing an operation in a system that it gives me as a result, for instance, a negative density matrix. So first example, paradigmatic is PPT. Okay, I say that I can apply, if I have a combined system, Alice and Bob, and I do just transposition in one of the subsystems, Bob, and my result is negative, this system is entangled. Okay? So that's what I'm saying. Well, this is the paradigmatic example of a map which is positive, but it's not completely positive. Because transposition is a positive map. Okay, so at the mathematical level, it's very easy. If I have a matrix and I transpose 5 by columns, the eigenvalues are invariant, it's the same. So if the eigenvalues were positive, they are positive. Okay, so this is a map which is positive. But if I do in a composite system, on Alice, do nothing, and on Bob, transpose. This doesn't have to be a completely positive map. Okay? And if the result is that it can be negative. So this is a typical example of a map which is positive and it's not completely positive. And this is why it's an entanglement criterion. So that was discovered the other way around, but then it was seen that it is like that. So Perez discovered this PPT, okay, and then Horodestis discovered that this corresponds to a map which is positive but not completely positive. Another example that maybe you have seen is a map which is of this form. It's called reduction map. So I take my state in rho and I do the following. In the case that the trace is 1, doesn't matter. Identity minus p times rho. So this map, it's k positive, but it's not k plus 1 positive for these values of p. That depends on that. Okay. So, which means that it can detect states which are entangled. Okay, because it's positive but not completely positive. And so now I can do the same that I was doing for the entanglement witnesses. I can say that a map can also be written as the composable map. And a map is a positive map. Okay? It's the composable if and only if I can write it like a positive map and another positive map which is composed with the transposition. So, E1 and E2 are completely positive maps, and D is the transposition map. So if a map can be written like that, I will say that this map is the composable. And of course, if a map cannot be written like that, I will say that this map is not the composable. Okay, so now I have a theorem. Okay, I say that a state, it's PPT entangled if and only if sufficient and necessary. Okay? There exists a map such that the map it's not completely positive because it has to detect it that it's entangled, and if on top of that it detects that the state is PPT entangled, it cannot be the composable. Okay? So any map which is not completely positive and it's not the composable, it's able to detect a state which is PPT entangled. So how can we solve our problem of determining if a state it's not? We have to know all possible maps. How many maps do they exist? Infinite. Okay, so you cannot start to put. Okay, so this is like always. So if you find a map which is not like that, fantastic. But if you want to find the opposite, so you say, okay, imagine, so maybe with PPT this is not enough. This map is not perfect. Okay, and I need to find another map. So I have a state. I do PPT, it's positive. Well, I don't know if it's entangled or not. Give me another map, which is not completely positive. And if this other map detects this state, okay, then the state is entangled. And if on top of that, this other map, it's not the composable, the state is PPT bound. And you have, okay? Although we know maps. So now, I wanted to go back and say, in C2, C2, and C2, C3, all the states PPT is sufficient and enough. Why? Well, because in the 70s, okay, Voronovich and I don't remember who else, mathematicians, they show that in C2, C2, and C2, C3, all the maps which are completely positive, okay, are all the maps which are non-completely positive are always the composable. Okay, there is not a map which is not the composable, doesn't exist. Therefore, that says that it cannot be entangled states of 2 qubits and 1 qubit and 1 qubit that they are MPT, bound entanglement. It's that important. This call we call it bound entanglement. Yes, it's important. We will not enter today here, but the fact that these states that they have entanglement and cannot be seen by PPT, they are very important. Okay? They have a lot of consequences. So, in C3, C3, are all the maps non-decomposable? No, they are maps which are all the maps decomposable? No, they are maps which are non-decomposable, all right? And these maps are able to see PPT bound entanglement. So in C3, C3, for 2 qubits, I have entanglement which is bound. But in general, I don't know how about these maps. Okay, so now, we have been talking about maps. We have been talking about entanglement witness. Now I want to link these two things. So because it sounds very casual, no? That I'm talking about maps which are not decomposable, maps which are not defined positive, entanglement witness which are operators. So remember, a map, it's not a matrix, okay? A map is a transformation on a density matrix. So I cannot write it like a matrix. Yeah? So when I have it's a quantum channel. So a map, for instance, a unitary map acting on a density matrix, like we were saying the first day, acts as U, rho, U diagonal. This is not a matrix. I have to put rho and U and U diagonal in the two sides. But a witness is an observable, it's a matrix. Okay? So how do I link these two things? Okay? There is a link between these two things? Yes, there is a link. and this is probably one of the most important things in quantum information theory, which says the following, okay? Given a map, which goes from the bound operators that they act on a Hilbert space HA to bound operators which they act on a Hilbert space HB, so from density matrices to density matrices, they don't have to be in the same Hilbert space, this is a mathematical concept, okay? There exists always associated an operator, J of lambda, which lives in the bounded operators of HA times HB, okay? Such that this operator, I can write it like identity acting on A, the map like that, and this acts on the unnormalized maximal entangled state which lives in HA times HA. What is this object? This is a matrix. So, what is this object? This is a map. What is HA? Imagine a qubit, okay? So, what is B of HA? This is a density matrix. If it's a qubit, a 2 by 2 density matrix, okay? So, I'm saying that I have a map that is acting on a 2 by 2 density matrices, and to this map, I can associate an operator which lives in this case, H. So it's a matrix 4 by 4, okay, which has this 4, okay? And this is very important, okay? So this is the choice of a map. And this is going to be an isomorphism. So I give you a map, okay, a unitary map, and I say, okay, find me which is this choice. And I can give you a choice map, something like that, a matrix, and say, okay, can you give me which is the map which corresponds to this choice? And this is the other part of the isomorphism. Conversely, that if I have an operator, this one of here, there exists always an associated map such that this map I will find it in the following way. I will trace over one of the systems, because remember that this guy lives in HA times HB, huge, okay? And the map only acts in one of these Hilbert space, so it has to be something smaller. Okay, so what do is I trace, I put this operator which I multiply by the transpose of this guy, the identity trace over A, and now I have my map. So it will be the same, almost, to talk about maps and to talk about operators, okay? And this is very important, and I have to put the transpose. Okay, so now I have an isomorphism. I don't care if I'm looking about maps or I look about operators. And this isomorphism looks like that. If my map is completely positive, okay, so I don't care about the trace preserving, my choice operator is positive semi-definite. If my map is a map which is real, physical, a quantum channel, an operator, so it's CPPT, completely positive and trace preserving, my corresponding operator has trace 1 and it's definite positive. If my map it's not completely positive, but it's decomposable, so it's able to detect empty state, my choice will not be completely definite positive, but will be an MPT entanglement witness. What this is the definition of an entanglement witness. An operator, which is admission, which is not defined positive, and which is decomposable. Okay? And finally, if my map it's not completely positive, okay, and it's non-decomposable, my associated choice will be PPT entanglement witness. And this is very strong connection. Okay, so because I told you that for me, personally, the best definition of something it's entangled is that there is an entanglement witness that detects it. So the best definition of something it's entangled, it's a mathematical definition, but it's like that. It's that there is a map which is not completely positive, that's it. So now this is a little bit tough, right? So I'm told it's the last day, so you will not see more. But now it's hardcore business, okay? So let's say my lecture has finished here, but now I want to go a little bit further because I have been talking about positive, capositive, and so on. Why am I saying that? Okay, because what we did 2 days ago, no, yesterday, we said, okay, there is this, we were doing this operational, or these measurements of entanglement and so on, and I wanted to say, it's this guy, it's entangled and so on. today and say, okay, you have to have a measure, we can put this measure, there are measures which are better and they are worse, they are very good for pure states but not so pure. For mixed states they are not good and so on, so they have this negativity, which of course negativity is a good measure. Well, it's a good measure maybe for a state which is MPT, but if the state is entangled in PPT, negativity is 0, okay, so it doesn't see anything. Okay, so now I can say, well, now I want not only to say, I want to detect if my state is entangled, my mixed state, bipartite is entangled, but I also want to say how entangled it is. Okay? So I want to use all these things now to show that I can also say something about how entangled it is. And in order to do that, what I'm going to do is the following. So for pure states, we have Schmidt number, okay, Schmidt rank, sorry. So we say with pure state bipartite, Schmidt rank gives everything. So what I'm going to do is, I'm going to do the same for mixed states. And I'm going to do that with what is called the extension roof, okay, the convex roof extension. So I make a drawing of this convex roof so that it's clear. So I have a convex set, which is this one. I have another convex set, which is this one. And the convex roof extension is how can I make these two sets convex. So I make this thing, okay, like the roof. Okay, so this is how I see it. And then this bigger set, it's convex. This is the convex roof extension of these two sets, okay? So one set with one point that doesn't belong to that. Okay, so I cannot join it in another way. I can join it also like that, or no, because it will not be convex, okay? So if I do something like that here, it will not be convex. So now I do the following. Given a mixed bipartite quantum state, I'm going to define what its Schmidt number. And I'm going to do it with this convex extension. I'm going to do, okay, we denote by K the Schmidt number of rho AB if it's the minimum over all the ensembles that generate rho AB of the maximal Schmidt rank of the pure ensemble, of the pure states in the ensemble. Okay, so let's see what it means. So I have a density matrix, and I say, you have a density matrix, you have many ensembles that realize this density matrix, okay? Now I want to say how much entanglement I have in this density matrix. So I will look over all possible ensembles that I have, and I will choose, of all these possible ensembles, okay, the infimum of all these possible ensembles, okay, and the maximum in each, or let's put it like that. I have my density matrix. I look at the ensembles. Imagine that there is only 3, which is not the case, of course. But I look at these 3, okay? And now I look which is the Schmidt rank on each of them. Okay, so in each of these ensembles, I have pure states, which are bipartite, and now I look which is the Schmidt rank of each of them. And imagine that in the first ensemble, I found that the Schmidt rank, there is one of the pure states which is there that has maximal Schmidt rank 5, and the other ones are smaller, 3, 2. Okay, so in this ensemble, how much entanglement I have to put? I have to put the Schmidt rank 5 to create it. Okay, so that. Now I look at the second ensemble, and in the second ensemble, I see that I have another decomposition, but all the pure states which are in this ensemble, they have at most Schmidt rank 3. Okay, so I already know that my density matrix, I can write it putting at most the Schmidt rank 3. This is my money, okay? So it cannot have Schmidt rank 5. It has a Schmidt rank 5. And now I have a third ensemble. And the third ensemble, I look which are the pure states, I calculate the Schmidt number of each of the pure states, and I found that the highest of one is 4. Okay, so what is my conclusion? The Schmidt rank of this density matrix is 3. Because there is at least one ensemble that at most is 3. Okay? So this is the Schmidt number. And this is a very good quantifier, except that the convex roof construction is horrible because I have to check all possible decompositions of my state. But what I'm talking about all these things, because I can do it in some way, okay? And this is what I wanted to say. So now I want to write my density, my space of operators like that. I have states, mixed, so pure states, remember, pure states that are here in the border and I know everything is a Schmidt rank. There is also rank efficient guys which are here. Well, here how it is written it would be possible, but they are. I don't care how them. They are measured zero out. Okay, I don't care. Now I have separable states. Schmidt rank 1. Okay, so any decomposition has Schmidt rank 1, so they are separable. The states that they have some entanglement, I can decompose it that they have the Schmidt number equal to. Of course, inside of the Schmidt number equal 2 are the ones which have Schmidt number equal 1. Schmidt number equal 3, and so on and so forth. Okay? So this is like this problem of the Russian dollies, right? You have one convex set inside of the other convex set, inside of the other convex set. And now I want to say, can I look for entanglement witness or maps of entanglement witness because it's an observable, so I go to an experimentalist and I say, listen, this is the observable, and then please construct it and measure. And it works. We did it many years ago, and it works. So the experimentalist did it, and we show something who has Schmidt rank 4 for the first time with Otfried. Who's Schmidt rank 4? Otfried is here preparing the lecture. Checking. With Otfried, okay? And the people from Copenhagen, and we did it like that. So now I'm going to redefine all my things. I will say, okay, a quantum state, okay, this means positive, but doesn't matter. A quantum state which lives in HHV has at most Schmidt number k, if and only if, for any k positive map, it holds that this is positive. Okay? So now I can use my witnesses or my maps, and now I'm not interested anymore in knowing if the state is decomposable and not decomposable. If I want to do that, I can also do it because I have to find a K-Schmidt witness or a K-Schmidt map that allows that it's non-decomposable with the depth, a state which has Schmidt plus 1 and it's not decomposable. Okay, so I joined all these pieces of the thing together, and I can do that. Okay, it's easy? No, it's very difficult. It's horrible, okay, but it works. Okay, so if you are able to find a map which is K positive and it's not decomposable, then you can find states which, and you can say how much entanglement your states will have. For instance, one thing that we know, but it's not proven because it's very difficult, and as far as I know, nobody knows how to prove it, is that if you take a state which is PPT bound and you say, which is the maximum, so imagine that I have C3, C3, maximal Schmidt rank 3, cannot have more, okay? Does exist PPT bound that it has a Schmidt rank 3 in 3? No. We suspect it doesn't exist. Prove it, we don't know how to prove it, okay? But we believe so. If some of you are like these problems, I have thousands of them, okay? So it's very nice. Okay. So now, can we do that and extend that to multipartite systems? Because this is a very powerful thing. Okay, so I have a state, I'm able to write a map. I know that there is an isomorphism, and I can write it as an operator. Listen, an operator which on top of that is a mission if the map is completely positive. So this is something that this is what we do in the experiments, no? To apply permission operators, observables. So these are observables. Can I extend that for multipartite? No. Okay? It's very hard, but not. Why not? Because all these concepts are bipartite. It's the identity times the map on something. So if I have 3 parties, I will have to do the identity plus the map on something. But this will be equivalent that I'm doing a bipartite splitting. So I have Alice, Bob, and Charlie, and I say identity in Alice, identity in Bob, and in Charlie I'm a, well, I'm sorry, I'm cheating because I'm doing Alice and Bob together, and Alice and Bob and Charlie apart. So I cannot do it. But if I want to do really a 3-partite, doesn't exist. Okay, mathematically it cannot be extended, or we don't know how to extend it. Okay, so we don't know how to do completely positive maps for multipartite systems and so on. So which makes multipartite. Somebody was asking why it's multipartite so difficult. Well, multipartite is super difficult because we don't have any of these tools. Okay, intrinsically it's difficult. Okay, qubits are easy because you have very small dimensions. Why qubits are easier? Well, easier because qubit, all the maps are decomposable, and we know how to do it. Okay, but we don't know how to do it already for big things. Can we fully characterize bipartite entanglement? No, not for the moment. Why? because the full characterization of quantum maps or the full characterization of entanglement weakness is NP-hard. So it doesn't matter. Whatever you switch in order to find how to solve this problem from another perspective, you know, if a problem is NP-hard and you know how to solve it, you will be able to solve all NP-hard problems, which, of course, it's not true that it cannot be solved, but it's very strange that it can be solved. But if you start with a problem which is NP-hard and you find something which is completely different, you end up that this problem that you are doing in a completely different way will be also NP-hard. Okay? So we cannot go further. And what I want to now, because I think I can give you a lot of information, and I would like to spend the last minute here on this thing of here. Okay? I want to show you what we have done in 3 years. Which is not bad. Okay? I'm sorry it's too small, but this is the things that we have to do. Okay? First, we learn how to describe a composite system, and we put the spell on composite, on tensor products. Okay, so this is what we did. Second, we learned what is the Schmidt decomposition of pure bipartite quantum states. Third, we say that in order to calculate the Schmidt decomposition, we'll have to look at the marginals of my pure state, and so it's very easy to calculate the Schmidt decomposition, and we know. And knowing the Schmidt decomposition, we know if a pure state, is entangled or it's separable. Then we say, okay, pure states are boring because we know everything, let's go to mixed states, and all of the mixed states are what happens normally. And we say, okay, how we describe mixed states? Well, we describe mixed states in the typical way, which is with one ensemble of pure states, okay? And now with that, and doing the convex roof, the first convex roof that we did is, okay, the set of quantum states is convex, and it has all these extremal points which are, this is the convex roof, so I take extremal points and I join in a convex way all the extremal points. This is the set of quantum states. Then, when we finish this thing of here, we say, okay, we want now to see what, this is the wrong order, so the right order will be see, okay, we have done that. Now I want to know if a mixed state is convex or it's entangled or not, but for some reason, which I don't know honestly why, I decided to go the other way around. I say, okay, I want to see how are the properties that if I want to know if assuming that the state is entangled, let me see how much entangled it is. Okay, and say, okay, let's define entanglement measurements. Let's give for pure states, which is the thing that we know what it's easy, which is entanglement measurement, and we say it's disentanglement entropy, and I told you, yes, it's like that, but it has a meaning. And the meaning is that only for pure states, bipartites and qubits, this is exactly equal to the entanglement cost, or the entanglement cost and the entanglement of distillation, which tells me how much EBITs, okay, or entanglement I have to put to do a task, or if I have a lot asymptotically of my states that you have produced in the lab, which task I will be able to do by distilling these things. So this entanglement entropy is operationally simple, so we like it, and it's meaningful, we like it. Okay, so this is a plus. Then we say that what happens when we have a mixed state, and we say, okay, for mixed states, but only for qubits, because in qubits everything, now somebody say, why it's different? Well, it's different because we know the maps at the end, okay? And this concurrence is related to the maps. Only for 2 qubits we can define an entanglement measurement which has sense, and it's full. With that we have enough, okay? It's the concurrence. And then we say, if we go out of these qubits, okay, we have qubits, how we are going to do it? I say, well, we can use negativity, which is very easy, and now today we say what is negativity and what is, so negativity is, I do my transformation, partial transpose, and I look how many negative values I have. If I have 0, negativity is 0, and then I add all the negative values, and this is a very good measure of entanglement. Okay? Then we put also some operational entanglement measurements and geometrical ones. Okay? We say we can have operational, we can have geometrical, and they are not corresponding one-to-one, but both of them they are useful, and we gave us some examples of that. Then today what we did, we introduced sufficient entanglement criteria, and in particular, say PPT. There are many others, okay? So if we write a note, we will put others, but this is the most powerful. So there are other criteria which correspond to other maps that they see states that PPT, the map corresponding to partial transposition, doesn't see. But in general, all the other ones are weaker, so we love PPT. Okay? And then we say, okay, that of course this is sufficient, but it's not enough. So it's sufficient to determine that it's separable. This is the reason why I always get confused. So it's sufficient to be separable, it's necessary for entanglement, and the other way around. So PPT is sufficient to ensure that it's separable and necessary. Then we show that there are states which are entangled, but they are PPT. I didn't give an example, but there are many. Okay, I even can write it like that because I work on that, so I know them by heart. Then we introduce entanglement witnesses because we say, okay, this is very good, but now, and this is also important, it's not only for fun. Because one thing which is very important is you are in the lab and you want to certify. You have to certify your state is entangled. Okay? Why you have to certify? Because there are protocols that they are based on that. And if you are not able to certify that the state that you are using is entangled, okay, you cannot ensure that the result of the result is good or not. Okay, so for instance, for quantum cryptography, if you want to use Ecker 91 protocol, okay, so how do you have to use how do you use in Ecker 91 protocol? Okay, you have to use bare inequalities to be sure that what you are sending is correct. So you have to certify these things. And entanglement witness is the way to do it, okay? Because it's unobservable. So we put entanglement witness. We show that there are quantum maps and completely positive quantum maps, which is the most general thing that you can have. We did a lot of things. So we define what is a K-positive map. We show that quantum maps can be linked to operators, which is the Choi-Jamelkovsky isomorphism. We show that MPT entangled states are detected by entanglement witness, which are non-decomposable, which are decomposable, and PPT are not decomposable. We define the Schmidt number of a mixed state and link its detection to the K-positive map. And we have not shown, I have not shown, okay, but I would like to tell you that what is the most funny thing of all these things. So I started by pure vectors, okay? I have a vector which lives in a Hilbert space. Then I put a density matrix, but the density matrix also lives in a Hilbert space. I can think my density matrix like a vector. Instead of writing as a matrix, I write it files, okay, in a column. And this is also a density matrix. And this is also a vector in a Hilbert space, okay? And now, I have operators that they act on, so operators that they act maps in a vector. But I can have super operators that they also act on my density matrix when I think my density matrix that it's also a matrix. And I can go 4 and 4 and 4 and 4 and get a lot of information like that. And this is what it's called the charge of the Hilbert spaces. Okay, I can go further and further. And so let me finish with that. So working on entanglement, okay, it's challenging, but it's worth. It's full of surprises, okay, so things that seem simple, they are very complex, and the other way around never happens. Something that is complex is never simple, okay. But it's very linked, and also yesterday, Alfred will say, to many fields of mathematics, which seems completely unrelated. So we are sorting through entanglement things of problems of mathematics, which, I don't know, I work in compositive matrices and optimization of non-convex sets through entanglement has nothing to do with quantum theory, okay? I didn't put any reference, but it's a Bible, okay, which is the Bible, so the charge of Hilbert space, the Bible of our charge is a review thing that it was written by Pavel Horodecki, Michael Horodecki, and Richard Horodecki, I think already in 99 or something like that. So the field has progressed a lot, but this is the Bible still, so the usual Bible is also quite old. So, but there is many other contributions, and in particular many contributions of Gottfried, which will tell you which are very important. So thank you very much for your attention.
Thank you very much. Questions?
Hi, thank you for the talk. There was a point that you mentioned a few times that I didn't get. You mentioned that usually you can have like multiple ensembles to describe a single density matrix. But like as far as I understand, if like all your eigenvalues are different, you get a unique eigendecomposition, and why can't you just take that as your ensemble?
The Schmidt, you mean?
Yeah.
Because the Schmidt only works for pure states. So, you are right to say,
Okay, you want to ask the following, but this is what we are doing. I have a mixed state, okay? I look at all possible decompositions of pure states. Each of the pure states that enters in the decomposition, I look for the Schmidt basis and tells me which is the Schmidt rank, okay? And then I do it for all of them, and I choose the decomposition, which I can write my density matrix, which has the smallest Schmidt rank of the states. This is exactly what we do, okay? But a priori, to calculate that, you have to calculate all possible decompositions of a density matrix. So let me give you the typical example, super simple example. 2 qubits, identity, okay, in the computational basis. 0, 0, so it's this matrix of here. Okay, so the identity, which is a state, obviously, it's a physical state, it's a time positive emission, trace 1, it's this, okay, of Alice and Bob. In the computational basis, 1, 1, 1, 1. Okay, so this is 0, 0, 0, 1, 1, 0, 1, 1. I have this decomposition, okay? In this decomposition, the Schmidt rank of each of the pure states that enter here, so now I write it in the 1 over 4, okay, so the density is 1, but it doesn't matter. So it says but it was not there. Okay, so how do I write this? Okay, the intensity of AB is this decomposition. 1 squared 4 of 0, 0, 0, 0, plus pam, pam, pam. Okay? So, I'm writing it like that, no? And now I say of this A, but I can write it, so this is rho AB, but if I write it as a thing, it's like that. Okay? It's 1/4 probability of all of them, pi, of the following thing, of the state 0, 0. Okay? All the probabilities. 1/4 of the 0, 1, of the 1, 0, of the 1, 1. Okay, this is a decomposition of this ensemble, and it's a Schmidt rank 1. So this guy is separable. Now I write rho of B. I can write it also like that. It's, again, 1/4, because this is another basis of maximally entangled states. The singlet, the 3 singlets, the triplets, sorry, plus, horrible, no, let me put it right. Okay. The identity, I can also write it like that. The identity on Alice and Bob, I can write it like the following. With probability all 1/4, I have the following states. 0, 0, plus 1, 1. 0, 0, minus 1, 1. 0, 1, plus 1, 0, and 0, 1, minus 1, 0. This is also the identity because it's a base. Schmidt rank 2. What is the Schmidt rank of the identity? 1, because it was another decomposition of the Schmidt rank 1. Okay? The problem is if I give you something and there are many other bases, no? Because if I now do a unitary, I will have another basis and another basis. So, also there is something that you have to, I don't know, maybe you know, okay? But how do I create an entangled state? Okay? I have so how in the lab you create an entangled state? So you take, for instance, something very simple, two spins, 0, 0, it's a product state. And now you apply a unitary. And then you get an entangled state. Okay, this is like that. Okay, so this is important. Now, this is different than if you do unitaries which are local. Okay, then you can do anything. But, so what I'm saying, it's very difficult to do and do these things because you have many compositions that they are equivalent.
Yeah, my doubt is because, like, I think this kind of degeneracy comes from the fact that in this example, all the eigenvalues of the density matrices are the same. Isn't that atypical?
No, I mean, this is typical of the identity because it's like that, okay? But because it's the identity, so it has to be proportional to 1. But in other cases, no, it will be different and it doesn't matter. No, in general, that will be different. It will be the compositions that they have different weights and different states under the composition.
Even when the weights are different?
Normally, the weights are different.
Yeah, okay, thank you.
Normally, the weights are... Listen, you have to take into account that when I do the decomposition, I'm not looking for an orthogonal basis.
Oh, okay.
No, the states don't have to be orthogonal at all. I'm just writing as this is the thing maybe that it's confusing. It's not an orthogonal basis. Yeah.
Thanks for the talks that you gave us. Something that I kept in mind was because you gave us the definition of what would be a quantifier of entanglement. So we had all the criteria. But when we see PPT that we're going to have negative numbers, when I have, let's say I have 2 different states and I use the PPT to check for entanglement. If I have someone that has like a more negative value than the other, doesn't this give me an idea of the strength of the entanglements that they have between them?
No.
No? Okay.
No, I don't think so. In some cases maybe, but in general no. So for instance, if I have negative and I use negativity, negativity is a measure. So if I have 2 states which are identical, which they live in C3, C3, okay, and one has negative eigen and so on, yes, this will be. But in general, okay, this doesn't have to go, so that's not the case. And of course, what it can, so also imagine it can happen the following, so you take a criteria. In your criteria A, your state doesn't show that it's entanglement. But in another criteria, it shows it's entanglement. The state obviously is entangled. Okay? But, the problem is that you will need infinite criteria to solve. Well, maybe there is another way much more intelligent to do it and we have never seen it. But a priori, how it is stated, this problem is that you need infinite criteria because there are infinite maps or infinite entanglement witness and so on. I mean, this is also very negative, right? So if you know something about the state, so you know more or less how to put entanglement witness and things like that. So it's not so difficult.
More questions?
Thanks for your talk. A bit of a religious question regarding the church. So you said that you can display any density operator as a vector. Can you then perform all of quantum mechanics with density matrices as vectors, for example, like open quantum systems and all of this? And can you display like Gauss operators in terms of matrices and all of this? So it's an isomorphism.
Yeah. This is a very nice way to do it, okay, a priori. So try to do this, and you can do it theoretically, yes, okay? But this is a way to do it, okay? So this is called vectorization, and it's quite used in, so it's very, well, if you do vectorization, for instance, it's relatively easy to distinguish between dissipation and the coherence and all these things, and you can see and all these maps. I mean, this is a full field of quantum info. Yeah, well, of quantum mechanics, sorry, not quantum info. Yes.
Thank you.
One final question.
Thank you very much for your talk. I have a question related to this geometrical picture. So, is it true that there is really a border between separable and inseparable states? And if so, then probably this states which belongs to the border should have some interesting properties. I don't know. Is
The
it-
ones which are in the border?
I mean, on the picture we have entitlement states. Like, I just interested if there is really a border, or it's just
Okay.
picture.
So if you are here, for instance.
Yes. for
Okay, I
example.
can tell you something that I have not told you because, of course, I didn't say anything about entanglement. But yes, there is something. So theoretically, you can know if a state is here or here. Okay, how? This is something which is called symmetric extension, and it's done with semi-definite programming. Okay, so you have your bipartite system, and you add the copy. So imagine that you have C3, C3, 2 qubits. You add an extra copy, 3 qubits now you have. Just to have an idea, 3 qubits means that you are dealing now with matrices which are 27 by 27, which is 3 to the 3, okay? 3, 6, 81 by 81, so that is say I'm doing the math. And then, now you have to look at the entanglement weakness and so on, okay, which is much bigger. So you can do it. And what do you realize? You realize the following. And this symmetric extension, it's a beautiful theorem that if your state is PPT entangled, okay, so it belongs to the yellow and not to the white, there is a moment in which you will see that the extension is MPT, okay? And now, do you know how many extensions do you have to do? Well, no, you don't know how many extensions, but you know something, okay? So you know that if you are here, in this border, normally you can see it relatively fast. And so this is different, because you are very close to MPT, all right? But if you go here, this hierarchy goes to, I don't know, okay, it can be, I don't know, order 2 million. Of course, this is numerically impossible, all right? Because more than 3 or 4 in any computer you cannot put it. Okay? But they are different. So the properties of these guys and the properties of these guys are different. And I think it was yesterday Ottfried that it was saying that there is this very nice paper which is 5 open problems in quantum information, and there is another. You are here, Ottfried. So and there was another paper which we use sometimes, all right, which is open problems in Ikoki in Innsbruck. Okay, you have a list of 25 open problems, and if you have a problem that you don't know how to solve, you put it there. Okay, say, okay, I have been trying to solve this problem and I don't know. And then you see this problem, the last time that it was some success, and that it was 15 years ago. Sometimes there is, I know how to solve this problem. So, and then you see that when you go to this list, and also what else you were saying, these guys, they have different properties, okay? And we are starting to understand actually. They have different properties and they can be used for different things. So it has a meaning instead.
Okay. Let's thank Professor again for the information.